I'm here today to present Drop the ROP, a fine-grained control flow integrity for the Linux kernel. So how's it go? I mean, how's Black Hat? It's fun, right? So many gifts. Okay, so this work, in this presentation, I'm going to introduce KCFI, which is de facto implementation of fine-grained control flow integrity for the Linux kernel. And this work was developed in collaboration between University of Campinas, which is my former university, Columbia University, and Brown University. And it was developed by my colleagues here enlisted, and by me. I am João Moreira. I'm a Brazilian dude here in Singapore. By the time we developed KCFI, I was a PhD candidate at the University of Campinas. Currently, I'm no longer a PhD student. Now I'm a PhD, thanks God. And I'm currently working as a live patching engineer at SUSE. So I'm still hacking the kernel and doing stuff related to, kernel itself and kernel source code. So let's get it on. So this is our agenda. This is basically what you're going to talk. First, we're going to do a quick review on kernel return-oriented programming and check out why this is a thing. And then I'm going to give a quick look at control flow integrity, showing its limitation and the no issues regarding CFI. CFI is such like a big name currently, but we have to pinpoint what are the problems behind CFI. And then I'm going to talk about KCFI itself, which is our implementation. I'm going to give some technical details regarding it. Then I'm going to talk about which are the improvements that KCFI brings over known CFI issues, and then you're going to talk a little bit regarding its performance. Okay, so we have to start talking from the beginning, and because of that, we have to talk about memory and safety bugs. And as most of you might know, memory bugs, memory problems may allow attackers to overwrite code pointers. So they may have control over code pointers, be it like a function pointer or a return address, which is on the stack. And because of that, they can achieve something that we call control flow hijacking. So basically, they are able to achieve arbitrary code execution. So imagine that there's like a function pointer in your memory, and an attacker finds a bug that allows him to overwrite whatever value he wants in memory. Then he can corrupt this function pointer, which is in memory, and redirect your code towards whatever he wants. Of course, as this is a big issue, there are like many mitigations for this problem. So first well-known mitigation is the write XOR execute policies. So basically this consists in whenever you have a memory page, this page is either writable or executable, but never both. So by doing something like this, you prevent an attacker, for example, to inject malicious payload in your data sections. So he's not going to put code there which is disguised as data, and then redirect control flow towards whatever he may have injected. So he's not allowed to do that anymore. We also have ASLR, which is address space layout randomization, which basically consists in whenever you run your program, the data structures and the functions, they are in different memory positions. And by doing that, you prevent an attacker from knowing the addresses of the things that he needs to corrupt, or from knowing where he needs to redirect control flow to. So this is sort of like some sort of obfuscation. Of course, that there are also ways to bypass these mitigations. So here we are talking first about code reuse attacks. So code reuse will basically exploit functions which are already in your program. So of course that you have a program, you have executable code in this program. So what an attacker will do, he will basically use this code which is already in memory to perform his deeds. So basically these memory pages which hold code, they are already marked as executable. So this won't be a problem for him to redirect code there. Also, we have like memory disclosure bugs that enable an attacker to read arbitrarily from memory, and by doing that, he's able to infer which are the addresses that he needs to corrupt, or places where he needs to point the code pointers to. So he's able to infer which is the randomization offset used by the ASLR and bypass this sort of protection. And specifically for the kernel setting, we have something that we call return to user attacks. So imagine that an attacker controls a process which is in user space. So he knows the addresses of everything inside this process. So and he also is able to control the page permissions in this process because he owns this process. And since he's able to do all that, whenever he can exploit a bug in the kernel space, in the kernel code, he can redirect the kernel execution flow towards the user space memory, thus bypassing both write XOR execute and the ASLR. So this is a big thing. Of course, that because of return to user attacks, some ideas were also proposed, and the most prominent is the strong address space isolation, which basically consists in preventing some sort of abuses. So for example, kernel code, the kernel context is never supposed to execute instructions which are in the user space. So this is obviously something abnormal and should be prevented. So because of that, we have these implementations that try to not allow this sort of thing. So if you're in the kernel context and you are trying to run instruction which is in a memory page marked as a user space page, you're not going to be able to do it. So this sort of thing is even implemented in hardware nowadays. You have Intel's SMAP, which is a hardware extension for preventing this sort of abuse. But because of these protections, because these protections are becoming really common, attackers developed something called ROP, which is return-oriented programming. And return-oriented programming will basically reuse code. So it's a code reuse attack, but it's actually, we will reuse it in a special way to achieve Turing-complete computation. So as I said, it's going to reuse kernel code, and it's going to use a concept that we call gadgets. So gadgets are actually small instruction sequences which are ended by an indirect branch. When we are talking about ROP, we are normally talking about the return instruction. And these gadgets can be freely chained through corrupting the stack. So imagine that an attacker can exploit a bug that allows him to overwrite your stack. And he's going to put a lot of return address there as he wants to. And he's going to redirect control flow to a gadget, which will run maybe 1 or 2 instructions, and then run a return. When it's running a return, it's going to take the next address from the stack, which is controlled by the attacker. Then the execution flow will go to another gadget that will run 1 or 2 instructions and then run a ret and things like this. So he's basically reusing the last instructions on each function, which is already present on the code. So let's see how it goes. So we want to run a ROP attack to actually bypass strong address space isolation. So basically what we want to do is we want to disable strong address space isolation, and then we want to return into user space. So imagine that an attacker has exploited a memory corruption bug and overwritten the stack with the values that he wants. And this first address, which is in the top of the stack here, is the address of this gadget. This gadget is like it's the last instructions in a function. So what this gadget will do, it will first run a pop rocks, right? And when it runs a pop rocks, what will it do? So execution was redirected there. So he will take the first value on the top of the stack and put it inside rocks, right? So basically rocks will contain the value that we call smap killer here. We call it smap killer because this value is the specific value that you must put into a control register to disable smap. So that's what we want to do. And when it runs the ret, what's it going to do? It will take the next address in the stack and redirect control flow there. And now it's the address of another gadget that will run mov rocks inside CR4. And notice here that CR4 is the control register that actually controls if smap is on or off. So basically we are setting the bits as we want. We are controlling CR4 by first controlling rocks. And then after disabling smap, what we're going to do is we are going to run a ret instruction, which will redirect the control flow to the address of our payload, which is actually in user space. So basically, this is how we get pwned. Okay, so what if we confine the indirect branches to save previously computed locations? So this is basically the idea behind control flow integrity. So The idea is originally indirect branches can redirect control flow to whatever they want, but preventing this sort of thing, preventing this kind of permissiveness is what we want to avoid when we implement something like control flow integrity. So basically, we are going to find which are the addresses that each indirect target should point to, and we are going to enforce this. So these paths, which are allowed, they are defined by the application's control flow graph. And of course, that there are different methodologies for computing and enforcing this control flow graph, like a CFG. So we have many different implementations that enforce this kind of thing. If I'm trying to do something like this, if I'm trying to enforce paths to a program, to the indirect branches, what could possibly go wrong? Well, first thing is relaxed permissiveness. So if you're enforcing paths for your program and you have a relaxed permissiveness, the execution flow is going to be not very determinant. And because of that, attackers may still find paths that allow them to exploit your program. Another problem, of course, is coverage. So if you have indirect branches which are not protected, then you won't be able to protect these specific branches. Then attackers might be able to exploit that specific branch and that specific address. Also, you have problems with false positives because, if your control flow graph is too tight, if you don't predict certain branches, then your system will raise false alerts and will tell you that something that is not an attack is actually an attack, and you don't want that. So first, speaking on granularity issues, in CFI we have two major classifications. We have the coarse grained CFI schemes and the fine-grained CFI schemes. So imagine this situation here. So we have a function A, which is calling a function B. So on coarse grained CFI, which is more permissive, you have like a function B and a function C, and these two functions are actually allowed to return to the instruction which is right after B, after call B. So in this scheme, you are not like enforcing that if this call is the call to the function B, only B can return here. No, whatever function may return to the instruction which is right after a call. So this is basically coarse grained CFI. And in fine-grained CFI, you have a more detailed CFG. So basically, if you have a call to B here, you will not allow C to return here. Because, this is a call to B, so C is not allowed to return there. Right? So, in fact, coarse grained CFI is known to be bypassable. Researchers have shown that this kind of protection is bypassable, and you can actually execute code arbitrarily even under these circumstances. Okay, now talking about KCFI, which is our implementation. It's a fine-grained CFI scheme for the Linux kernel. It's based on instrumentation. We use LLVM, which is a compiler for doing this instrumentation. The CFG that we use, that we enforce, it's computed statically. So basically what we do is we do some sort of source code analysis. We run a full compilation round doing analysis on the source code that we are actually compiling, and we figured out things like prototypes for pointers, prototypes for functions. And then on the generated binary, we run a binary analysis where you can figure out more stuff like solving aliases, like identifying which function is actually calling another function, how the inlining is resolved by the compiler, and things like this. Okay, so how exactly do we compute a control flow graph? We have basically two major problems here to solve. First problem are the backward edges. So we're talking about return instructions. We need to know which are the places to which a return instruction can return to. So it's kind of easy to compute because all you have to do is to take a look at the final binary. So if you have a function A that calls a function B, you know that the function B must return to the function A whenever it's returning. So it's kind of easy. It's already a solved problem. But we also have the forward edges, which are like the indirect calls. And for these cases, it's a little bit more complicated because a points-to analysis is a mathematically unfeasible problem, so it's incomplete. You cannot just take a look at the source code and say, oh, this function pointer will call these, and these address. You cannot do that precisely. So you have to do some sort of heuristics here. And what we do is that, we follow the approach which was originally proposed by Abadi et al. I mean, this is the guy who originally proposed CFI in 2005. He's a researcher from Microsoft Researcher, or was. I don't know if he's still there. But in his approach, basically what he says that if you have a function pointer, and this function pointer has a prototype. If you have a function, this function has a prototype, then you enforce that these prototypes must match in a way for this call to happen. So if you have, for example, a function which is void and receives no arguments, a function pointer that is void and receives no arguments, this function pointer can only be used to call functions which are void and which will return void and receive no arguments. So you enforce this sort of matching. And by doing something like this, we are actually clustering functions by prototype. So you have a specific prototype, all the functions on that same prototype will be allowed to be called through that function pointer which matches this prototype. So just to make it clear, we have an example here. So we have this function pointer here which is FPTR. It's a function pointer of the type that returns a float and receives an int as an argument. And using this function pointer, we can call the function dog and the function cat because they have the same prototype. They're returning float and they're receiving an int as argument. But you cannot use this function pointer to call the function fish because it has a different prototype. Okay, so I think it makes it clear. After building the CFG, we need to enforce it. So what do we do to enforce it? Then we recompile the kernel code with the CFG in place, and we instrument the generated code with whatever we need. So we're basically going to use two different kinds of primitives for instrumentation here. First, imagine this code here. I mean, originally the original function only had this call, which happens through a register here. It is an indirect call. And we want to protect this indirect call. So what are we going to do? I think you cannot see the word here very well, but try your best. So what we're going to do is, before actually calling the value which is in the register, what we're going to do is we're going to the reference, the value which is inside the address, add an offset of 4 in it just to bypass the opcode. We'll go to it and see if the value which is there is actually a value that we expect. So the functions that are allowed to be called through this call instruction here, they have as their first instruction a NOP instruction, which is an instruction that does not perform anything, but that actually allows you to encode values inside of it. So this is actually working as a watermark. So we are actually watermarking the functions on their first instruction. So we are putting a value there that's going to be checked before calling the instruction, before calling the function through that specific register. So if the value compared here match with the value which is here, then this jump is taken. What makes the control flow jump to here, and then the call happens. If this is not the case, then we are pushing the value which was the referenced just as an argument for a violation handler function. And then we call what we call a call violation handler, which is a function that will actually raise an alert and let your sysadmin know that something nasty is going on. So that's more or less how it happens. So here we have what we call like a guard instrumentation or a check, and here is what we call a tag. So this is a watermark instrumentation. After that, we have, we also need to protect the returns, as I said, and the instrumentation is pretty similar. So we have a call to function F1 here, then we're going to put a tag right after the call. And when F1, before F1 returns, it's going to run a check, which first will load the address, the return address, which is in the topmost address of the stack, into a register, and then we're going to dereference it and check if the values match. If they do match, we do the jump here and return. If they do not match, we call the red violation handler. So the idea is pretty much the same, except that we need to load the address from the stack, because it's not like in an actual register that we are calling or something like this. So is this approach really fine-grained? Is it like really safe or something? Well, at least it is fine-grained, and of course it is better than the coarse-grained approach which were proposed in the past. But yet we can still do better. We can do it a little bit further. So the presented scheme is actually prone to a problem that we identified and that we call transitive clustering relaxation. So although this name is quite complex, the problem is really simple. So let's see what is it. Imagine that you have a target for an indirect call. which is called both directly and indirectly. So as these targets for indirect calls, as they are clustered, so they will have, all these functions will have the same tags on their prologues, and they will check for the same tags before returning. So imagine this situation. You have a function A, which directly calls a function B, and you have a function C, which has the same prototype of B. So these two functions have the same prototype, thus they are clustered, and you have A calling B. Then because of the clustering thing, C can return to B, because the tag that will be in A, C can return to the B's call site in A, because the tag which is in A is the same tag that B will check when B is returning. So you have an allowed edge here that was not supposed to exist, which is C returning to A. So this is basically source code that describes the situation. You have a function A which calls B, then you have a tag here, and you have another function that can call both B and C through a pointer. And it must have the same tag here, because this tag will be checked when these functions return, right? So both B and C must check the same tag, because they both must return here. But the thing is, this is a direct call to B, even though C can still return there, right? So this is something that we wanted to prevent, because this is a necessary relaxation of our scheme. So in our code base, on the kernel configuration that we tested this thing, only for the void with no arguments prototype, we have 10,645 call sites with 4,484 void functions. So this is a lot. Even though, I mean, we still have other prototypes that add to that in terms of relaxation too. So this CFG, this resulting CFG is quite permissive. So yes, we don't want that. We want to find a way to prevent that. So the way we fix this is by proposing a technique that we call the call graph detaching. So call graph detection is also really simple. So first thing we do is that we identify the functions which are callable both directly and indirectly. Thus, we check the source code to see if there's a function pointer with the prototype for that specific function, and we also check the binary to see if that function is eventually called directly. And if this is the case, we clone this function. So we make a copy of this function in the resulting binary. And then the direct calls to the function, they are replaced with calls to the clone. So all the direct calls now will go to the clone and not to the original function. And the clone has a unique tag, which is different from the cluster tag. So this will result in something which is more or less like this. So we have a function A, which now calls bclone, and we have this word that code here. We have this Z function that can call both B and C through the pointer. Thus they will put the tag for the prototype here. And both B and C, they still check for the same tag before returning. But now we have a B clone here that checks for a different tag, and the B clone is actually who is being called on A. So actually C is no longer allowed to return here. So that's more or less how we solve this transitive clustering relaxation problem. So by doing this, the allowed call sites reduce it to 220 for indirectly called void functions. So as you can see, this is a meaningful optimization. I mean, we did some advancement here. And of course, this happens because we have no more transitiveness. Something else which is important and that we did implement in CFI is the support for assembly code. If you don't support assembly code, then first thing you're going to get a lot of false positives. Because if you are indirectly calling assembly code, you won't have the tags there. Also, if you have assembly code calling C functions, you won't have the tags there. Thus, the checks will raise the false alerts. Also, and even worse, the indirect branches in the assembly code will be unprotected, and this may be a target for attackers to exploit your system. So you have to support that. What we do is that, we wrote like a bunch of parsers in Lua. Lua, for those who don't know, is a great language developed by Brazilian guys, so I really approve it. It's Lua-based parsers that we implemented to automatically rewrite source code. So what we do is We have these parsers, we feed the assembly code to the parsers, and we automatically rewrite it, placing the proper tags wherever they should be. We replace a few macros in the kernel that, for example, in the kernel you have a macro called entry, which is used to mark the beginning of an assembly function. Then we have like a new macro that we call entry CFI that also marks the beginning of a function, but also places the tag there and things like this. So we do all this sort of tricks. And of course, there are a few handcrafted fixes that we needed to solve by hand because the kernel code is kind of weird, and you have like code which is generated by macros, and lots and lots and lots of very known pattern recognizable approaches. We evaluated this thing with 3 benchmarks. First, we instrumented spec 2006 with KCFI, so we compiled it with the checks. And we verified an average of 2% overhead on it. Of course, this is not very representative because spec is very CPU intensive. So you don't have like many branches there. So you're not really stressing your mechanism. So something else we did was like we compiled the kernel with the protections, and then we did execute LM bench on top of this kernel. The LM bench is like a micro benchmark. So as a micro benchmark, it is expected that it will have like very high overheads. Sorry, it's a micro benchmark. It's expected that it will have like very large overheads. So as a micro benchmark, what it will do, it will basically run a syscall or just like a TCP functionality or something very simple, which is an functionality from the kernel. And we have seen an average of 8% overhead on it. And we also did run Phoronix on top of this instrumented kernel. Phoronix is actually the macro benchmark. So basically what Phoronix is, Phoronix has a bunch of servers like HTTP servers, FTP servers. It has applications that will compress a file and do tasks which resemble more what you do in your daily uses on a server or on a computer. So it's expected that this kind of benchmark will have a lower overhead because it will run more code in user space, which is not instrumented. So we have seen a 2% overhead on average for this one. And of course, I can provide more details regarding the benchmarks. I have some slides about it on the back part of the slides. I just don't want to go into unnecessary detail now. Of course, that Finegrained CFI is not perfect either. So last year, some guys proposed, they have presented these papers in Usenix and CCS, showing that there are cases where CFI is still vulnerable to attacks. Of course, that these attacks are very specific and very constrained. And there's like there's this non-controlled data attacks, which are attacks that actually may allow an attacker to run code arbitrarily, but they're not literally like targeting controlled data like function pointers or return addresses, for example. And here in Black Hat Asia, I think we have 2 talks regarding it. I think that there was one talk right before mine that was regarding Microsoft Edge, and there's going to be another talk tomorrow. So this is sort of like a trend in the academia. These guys are looking for different ways of exploiting systems, even though they are using KCFI, as more and more people are using KCFI daily. So the complexity, actually the complexity behind these methods, they show that CFI is actually a relevant method. So, these attacks are quite complex. We don't know if they're like really usable on a daily basis. None of these attacks have ever been shown for the kernel setting. So I don't know. This at least shows that CFI is a meaningful protection, possibly more meaningful than ASLR. Okay, so now let's go see a demo. I'll try to run it live, but of course, I am an unlucky guy. Things go wrong with me all the time. So what I'm going to do is that I'm going to run a kernel here, which is instrumented with KCFI, and I have like a handcrafted exploit in this thing, and I'm able to control a function pointer through a synthetic exploit or something like this. So what I'm going to do is that I'm going to log into this machine. And I'm going to overwrite this function pointer. Are you guys able to read? Do you need to larger font or something? Larger? Okay. I just don't know where to do it. Sorry? Command plus? Awesome. Thank you. I'm actually learning something here. Now, is it better? Want bigger? Okay. So basically, we have this three interfaces that I have created through the BugFS here, and whenever I put some value inside over func pointer, this is going to actually replace a function pointer which is running on kernel. And whenever I put something on invoke function, this function pointer will be invoked. So it is not really an exploit, but it will show us what we want to see. So I also changed my module to show me which are the addresses of the functions which I want to check because I'm lazy. So we have these two functions. One is called allowed. Allowed has the same prototype of the function pointer that we are going to corrupt. And not allowed does not have the same prototype. It has a different prototype, thus it may raise an alert. So what I'm going to do first is that I'm going to put the address of allowed inside the function pointer. And now I'm going to invoke it. And I'm going to run the mask and see we executed the function here and here, and there was like no alerts raised. Now I'm going to execute the not allowed function, and I'm going to show you that when the prototype is different, the scheme really works. But before doing that, I want to show you like really how this thing works. So I'm going to plug GDB into the kernel and do a step-by-step execution of the whole thing. So okay, now I just plug it into the GDB. As you can see, it's paused. So I'm going to disassembly the function invoke function, which is the function which will be called whenever we do that echo one into invoke func. And the call which is actually being exploited is happening right here. So this call which happens through RAX. As you can see, the instructions on top of it are actually those instructions which I showed earlier for the instrumentation. And okay, so I'm going to put a breakpoint right here and put the kernel to run. I'll have to log in again because kernel was stopped and the connection dropped. And now I'm going to put the address of the function which is not allowed into the over function pointer interface. And now I'm going to invoke this function pointer, which is going to trigger the breakpoint on the other screen. So just like I said. So first thing we have here is an instruction which is actually loading the address, I mean the value which is in the register which will be used for the indirect call into RCX. Okay, so RCX now holds the address which will be used for calling, right? So what we're going to do is that what I'm going to show is that I'm going to show you what's there. So we're going to dereference it just like it's going to be done in this specific instruction here. So we have to dereference this address. But the thing is, as I told you before, this word is encoded inside an op instruction. So we have to do to add a small offset to it just to bypass the opcode, which is an offset of 4. And then we see that it actually holds the value 0710075A. If we disassembly the not allowed function, we can see that the same value is in the first instruction of the function. So actually, as the CMP instruction is actually looking for a different value, the value which it is looking is 91.2F5227. Then this is not going to be a match. So if we run a step here, we're going to the jump on equal instruction, and but the thing is not equal, right? So as you can see here in the debugger, the jump will not be taken. So we're going to go to the next instruction. The jump was not taken. Now we're going to push this value of the indirect call into the stack. And then we are going to call the call violation handler. The call violation handler is a really simple function. I mean, you can implement it however you want. Currently, it's only programmed to give you an alert. So I'm just going to hit continue here. And the code is now running again. And when I log in again, if I run a dmask here, as you can see, there's this CFI-C, which is actually the let's say acronym for a CFI call violation or something like this. And we have these two addresses, which is the address that triggered the violation and the address which was being called by the triggered violation. So we were able to map what exactly the guy was trying to run when he did this pointer corruption. So and of course, I mean, we did not block the function, but we could have done this inside the violation handler, and the function just printed that this function should not be allowed. As the tag after the function pointer was also different from the tag inside the not allowed function, we also have like a return violation that was triggered here. And well, that's it. That's pretty much how the scheme works. We could see it like step by step. Now back to the slides. I hope my friend Trump liked it and does not block me from joining the USA again. Okay, so what are the conclusions that we have here? So Finegrained CFI in the OS context is achievable. I think this is cool because the guys that presented right before me, they just had the same soundbite, you know, like, oh, actually doing a SSH cover channel through caches is achievable. So I think that most people are here trying to prove stuff. That's cool. We proved the stuff. Awesome work, guys. So CFI can be used to provide a meaningful level of protection, as we can see by the complexity of the attacks which are actually targeting CFI. And it will push attackers for more constrained and complex exploitation techniques. Also, current existing methods for refining granularity in CFI, they can and they must be improved. So as I have shown you, call graph detaching is like this is a new technique. Nobody have proposed that before. And by doing that, we actually refine significantly the fine-grained CFI schemes. So I guess that's it. I think I was like super fast. So we have like 1,000 hours for. I mean, I don't have like a very cool song like they do, but we can sing one here. Go on, guy.
You are using the same tags for every boot?
For every boot?
Yes. I mean,
if they are randomized or something? Yeah. No. I mean, they're not randomized because we don't. It doesn't matter. I mean. The scheme that we implemented, we do not rely on secrecy. I mean, the idea is that even though we were able to disclose memory, I mean, the tags and the verifications will still there, so we won't be able to redirect code whatever you want to. I mean, we are considering that a threat model where, for example, in your kernel, the guy won't be able to inject executable code into your memory. So, I mean, if he's able to put data there, it's data. It's not marked as executable. So he will not be able to bypass this kind of thing. Go ahead.
We need to protect calls to violation handlers.
Okay, protect calls from violation handlers. It would be required if we had, because I mean it's a direct call, so the violation handler is eventually returning, and there could be like a bug inside the violation handler that would allow somebody to corrupt the return from the violation handler. Yeah, it could be possible, but what I'm considering is that as my violation handler is really simple and very, very tight, that there's not a bug there. But definitely yes. I mean, if there's a bug inside the violation handler, the guy will be able to corrupt the return from the violation handler. But here comes something, right? So the violation handler was already invoked. So the sysadmin already knows that something is happening. So and whenever the violation handler is returning, the guy would maybe get the control of the system more.
Or we need violation handler to violation handler.
Yes, sort of. Introspection. Please.
How to handle interrupt handlers?
What do you mean by intra-handlers?
I mean, for example, a clock interrupt and then you can adjust the clock interrupt and then you return.
So, sorry, I could not understand. Can you talk a little bit louder?
For example, hardware interrupt handlers. How do you handle those cases? Because those interrupts are normal flow.
Sorry, I still not able to understand your question. No, please. I want to go for it. Hardware interruption. Okay, so whenever I have like a hardware interruption, so thing is the kernel will start executing through like an iGate or something like that, and it starts executing normally. So we don't really verify if the interruption is really running through, let's say, a protected gate or something like that. So we just assume that, okay, there's a hardware interrupt here, then we have like the interrupt handler here, the interrupt handler starts executing here. So we assume that this is safe because we don't know much of how an attack would be able to protect against this. And then this handler starts executing, and imagine that you have like another interrupt that will start executing. That's what you call like an interruption handler, right? So the thing is, this scheme does not really rely on the context of the execution. So that execution flow just stops, and I mean it's just frozen, just like it happens normally on the kernel. And the new thread starts executing, and it's irrespective to the previous one. So this new code will just start executing, and whenever it's calling new functions indirectly or returning, I mean this will be already solved. So I mean, it's not really a problem to freeze one execution and start executing another one. So the whole scheme is already, let's say, compliant with interruption requirements. Anyone else? Okay, so we have like a slide about it here somewhere. So for KCFI, without the CGD optimization, we have like a 2% space overhead, and we are talking about a kernel that has 718 megabyte. So it raised it to 718 megabyte from 705. If we do the CGD optimization, then our cloning functions, thus the overhead is bigger. Then we get like a 4% space overhead. So just to let you know, I mean the code base we used had like 132,972 functions, and we cloned 17,000 functions, 17,779. So in terms of numbers, it's considerable, but still not that much size overhead. Of course, that I don't know, something I would like to assess sometime is like if this has a meaningful impact in power consumption, because I mean when we talk about size overhead, we eventually end up talking about embedded devices or something like this, and these guys have a special criteria for power consumption. And I know that, for example, having the CGD optimization is something that will harm at least slightly your cache. Because if you were calling the same function indirectly and directly, I mean the same code would be in the cache, and it would be a cache hit. But now that you have like detached these things, I mean your cache considers these things to be different, so it won't be a cache hit anymore. So I would like to see it sometime. I just did not it yet. Please. We implemented it specifically for the x86-64 architecture. The x86 architecture has a few features that we use. For example, the tags that we used, which I showed you, they're implemented as they're not here. So they're implemented as not-else instructions, right? So not-else instructions. They're not like available. I mean, the instructions they are available in most architectures, but not all of them will allow you to encode the value inside of it. So this is something that we are able to achieve in the x86-64 architecture. So I believe that for other architectures, of course, there's going to be different constraints, but I think that currently the most let's say break that for implementing this thing into a different architecture would be having a way for encoding tags properly. We actually, I mean, we know a different way of encoding tags, which actually consists in declaring a global variable in the kernel and then doing a move instruction inside this global variable. So the value which is being moved is the tag, and the global variable is never going to be used. So it's just a way to do a dummy move with a value that we want to be there. But the problem is this scheme causes more cache contention. This scheme will harm your performance more strictly than using ops. But I mean, this is a way, for example, to implement this thing on a different architecture. Another thing which is interesting is that higher level caches, they are inclusive. So one thing is that, for example, when you are dereferencing an address for verifying if a tag is there, then if this address which you're dereferencing is not in the cache, then what's going to happen is that it's going to come into the cache as data. So it's going to be probably in L2 if I'm not wrong, at least. And then when you're jumping to this instruction to execute it, then it's going to be loaded from L2 cache and not from the memory itself. So the scheme, considering the Intel's architecture for caches, is really efficient. I'm not sure how it would perform on different architectures. More questions? Okay, great then. Thank you very much for coming. Thank you for your time.